Okay. So if you don't have any question regarding the material I give it to you so far, what we can do, we can move on with the rest of the material for the chapter 1. Okay, so we are towards finishing the chapter basically. And what we can talk about, we need to talk about some way of presenting the data. Okay, what does it mean? So computer, it has something called unsigned data. Unsigned data. While for certain applications, we will need to have something else is called signed data. So we have unsigned data and we have signed data. So now we have signed data. The one who invented the computer is human like us, right? So end of the day for him, he's following the human way of thinking, right? So he's trying to put a regulation. And what this regulation is? So for us, if we would like to say, I have a certain data I would like to add or subtract or multiply or so on, what I need to do, I need to represent it in binary. As we agreed now, everything in the computer is binary, right? Computer just like a bunch of wires, on, off, on, off, on, off. You know, the quantum computers is basically also on, off, but, you know, in a different way. But still, you know, there is on, off mechanism happening, you know? So anyway, if I have a certain number in decimal, the way that, you know, we represent and, you know, the way that, you know, we work every day, that means, you know, we're gonna represent it in a bunch of digits, right? In the binary form. So for instance, you know, maybe I have a number like this, 10101000, something like that, right? This is just a number I have in my hand. So people come and say, if you would like to represent this number, in unsigned form, so that means, you know, every single digit in front of you is contributing into the conversion of this in decimal. What does it mean? It means the following. Normal computer, they work in something is called 8-bit, 16-bit, 1 second, I'm sorry about that, 16-bit, and 32-bit architecture, and even, you know, there's something called 64-bit architecture. Okay? What is bit for us? Bit is a digit. Bit for us is digit. Okay? So the example I wrote it up here, how many bits we have is basically 1, 2, 3, 4, 5, 6, 7. So I have 7 bits representing a number. Okay? Let's say that, you know, I'm gonna make it 8-bit. This is not a Bible. That means, you know, I can change. I can make it 5-bit, whatever. Let's just stick with 8-bit for now, okay? So I would like to represent this value in 8-bit. 8-bit, so that means this number, if it's 8 bits, it has B0, B1 up to B7. So that means this number can represent up to what? 2 power 8. What does it mean? If I have an 8-bit, right? Like this, B0, B1, B2, B3, B4, B5, B6, and B7, right? This combination can be filling zeros or can be filling 1 or something in the middle, right? So that can be 0, 0, 0, 0, 0, 0, 0, 0. Or it can be any combination up to 1, 1, 1, 1, 1, 1, 1, 1, 1. 1, 2, 3, 4, 5, 6, 7, 8. I'm sorry about that. Okay. So what does it mean? It means that every single digit or bit in the number is representing to me what? Value. So if I said that, you know, I have this 8-bit representing unsigned, so that means this 8-bit capacity is from 0 to 255. Because, you know, this, if you converted like 2 power 0, 2 power 1 up to 2 power 7, they're going to be giving you 255. And this is giving you 0. So the range number we have here is 256. Sounds good? And it's unsigned. That means it doesn't have what? It's not positive or negative. It's just a value. Now, let's switch the gear to signed, right? So the mathematicians who built the trick, he said, okay, hold on. I have 8-bit here, right? This one. I have this 8-bit. I can just take one of these bits to represent my sign. And the rest will be what? Value. And they came into a conclusion, say this one is called LSB, which is the least significant bit. And this is called MSB, which is the most significant bit. And they say, okay, let's be, as a scientist, follow one rule. And this rule, why people just keep coming? Okay, following a rule saying that, we have the most significant bit is representing what? The sign. Okay, so the scientists came and say, make this one is the sign. Sounds good? Then they came and say, if we write 0 in this location, so that means the rest of this is representing positive value. While if we convert it to 1, so that will be a negative value written there. Okay, we're gonna make examples. Anyway, there is pros and cons of this trick, right? The pros here that, oh, okay, we fixed a way to present number and we already have a positive and negative, and we figure out that, we can put the most significant bit to representing the sign, right? The cons, this number is no longer having a bigger size of numbers to be representing. It's not like 0 to 155 positive, for instance, right? It's gonna be a vary from what? From positive and negative, and it's gonna have a mix. So example here. Let's stick with 8-bit. If I write 1, 0, 0, 1, 2, 3, 4, 5, 6, 7, 8, and I tell you this is unsigned value. So what you're gonna write? You're gonna convert this to me and tell me in decimal, this is representing what? 2 power 0, 2 power 1, 2 power 2, 2 power 3. So this is basically 8 plus 1, so this is 9. Just 9. But if I take the same number in front of you and I write it like this, 1, 0, 0, 1, 1, 2, 3, 4, and I tell you this is signed value, what are you gonna do? You will come and say, oh, most significant is 1, so this is negative, and this is the value in front of me, 9, so this is negative 9. What about if I tell you this is 1, 0, 0, 1, 0, 0, 0, 0, and I tell you this is assigned value? What you're gonna say? Okay, this is the bit is equal 0, so this is for me positive, and the rest here is 9, so this is positive 9. Any questions so far?
So 1, 2, 3, 4, 5, 6. You have 7. So
7. 1, 2, 3, 4, 5, 6, 7, and this is 8.
Okay, so the one all at the front just represents the sign.
No matter, it's 8. But when I say it's a sign, that means one of the bits have been now take caring of the sign and the rest are value. If it's unsigned, that means all 8 bits will be contributing in the number.
Oh, okay.
That makes sense?
Yeah.
So, Professor?
Yes, sir.
If we wanted to represent the maximum value with 8 bits, but doing it signed, we would need an extra bit so
exactly.
that we would...
Yes,
okay.
You're right. You're right. So in that case, I will just say 9-bit, and then, it will completely change the value. So conclusion, if I'm thinking about 8-bit, right? And I say 8-bit unsigned, 8-bit. So that means that thing, it's holding these values. We call it in the circuit level later on, we call it register, which is storing data, okay? So we call it register. Just hear this word and later on you will understand what's register. So whatever is holding this frame of number of bits is called register. So we say this register holding 8 bits is representing a vary value from 0 to 255, right? because it's 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Right? Then if it's signed, I will come and say different, right? I will come and say this thing is actually vary from positive 127, right? Because the first 7-bit is 2 power 7, so that's the highest one, right? Up to the negative 127, and there is 0 in the middle. But somebody will come and tell me, what? There is a situation I will have positive 0 and negative 0. Right? Let's make a scenario for this. Look, I have an 8-bit, right? If I write it like this, 1, 2, 3, 4, 5, 6, 7, 1, and I tell you this is sine. What is this actually representing to me? It's representing to me negative 0. Right? This is negative 0. And if I write it to you like this, 1, 2, 3, 4, 5, 6, 7, and I put here 0, then I'm representing to you positive 0. Is there anything called positive 0 and negative 0? That's actually one also from the drawbacks of the system. Okay? That makes sense? Because we are humans, we are not gods here, so we are not building stuff like an ultimate way or a higher level way. I don't know. How can you call it that?
Professor?
Yes.
Why is it starting from 127 instead of 128?
That's a very good question. So if you already have 8-bit, right? And you put here 1, 2, 3, 4, 5, 6, 7, 0. Okay? Can you please calculate for me what the value will be? It's going to be 2 power 0, 2 power 1, 2 power 2, 2 power 3, 2 power 4, 2 power 5, 2 power 6, right? And this is what? This is out because this is a sign, right?
Yes.
Combine them together, going to be what? So going to be here 1 plus 2 plus 4 plus 8 plus 16, right? Plus 32 plus 64. So they're going to be 7, 8, 15 plus 16 plus 6, 9, right? So 5 plus 6 is what? 11 was 1, 7, right? And then you add, it can be 127.
Yeah.
That makes sense?
Okay.
Okie. Anyway.
Sorry, can you repeat the part that says like the 1 and the negative 0 and the positive 0 is the same thing?
Have you heard about something called negative 0?
No.
Have you heard about something called positive 0?
Nope.
That's it. Thank you.
So you just negate it?
No, by the way, for the logic system, there is positive 0 and negative 0.
Oh.
That does not exist. It's like, I will tell you something. Why we are called a College of Engineering? We are studying mathematics, and we are actually combining it with physics to build a certain prototype. So we are not physicists, we are not mathematicians. We are taking both. I mean,
we're special.
Yeah, mathematicians, they believe in what's called unreachable solutions. While physicists, they don't believe in it. For us, we can believe in it if it will give me a product.
Yeah.
That makes sense?
True. That's true.
Yeah. Okay. Anyway, so far, what I mentioned makes sense? If it makes sense, I will move forward to the next step. If it makes sense, should I move forward or should I wait and clarify something?
So just as like a quick thing. So if we do use the signed bit, does that give us like an extra value to represent because we have the negative 0 or the positive 0, while with an unsigned, you would still have 255?
255
values?
maximum, yes. 0 to 255.
But with the
with signed, you're gonna have negative 127, positive 127, and 0 in the middle, right?
Right.
Yes. So did you see, you already have a very number, but in total will be the same number. I mean, the same number of numbers. You know what I mean? But then, it gives you more varieties, basically. Anyway,
Okay.
now we need to learn, we mentioned before, so there's something is called complement. And we learn that, complement using for what? Subtraction. I mean, one of the possibilities is subtraction. Of course, it's used for other stuff, okay? There is actually a side of branch of science that's called cryptography. Have you guys heard about it? My PhD, it was in cryptography, but anyway, it's a lot of weird stuff like that. And, if you look at it, it doesn't make any sense, but in reality, it makes sense. Anyway, now, if I have something called Sine magnitude, what is Sine magnitude? So I have decimal numbers represented in a positive or negative, as it's actually going to be translated to be sign value, right? What will be the equivalency of the first complement, second complement, as we are moving into binary? And what will be the signed magnitude out of it? That's a very good practice. And by the way, 99% of any midterms, first midterms, and questions and stuff like that, they ask these questions. It's a practice, when I started teaching, I was asking this question, but it should be fundamental, so nobody should ask, but it happens, So example, for instance, right? If somebody gives you a positive value like 7 and is asking you to give him the first complement of this positive 7, imagine what the value would be.
Would that be 8?
It would be positive 7.
No.
There is no complements for positive values. So you're going to take it as it is. When you say signed magnitude, that means I don't care about the sign, right? I just care about the value. So it's going to be a positive for me also. It's going to be 1, 1, 0. So look, I represented the 1, 1 like this, and I represented like that if it's in a 4-bit representation. That makes sense? Let's go into the first complement, second complement. First complement, this is a positive value. It should be the same. So it's going to be this complement of it, same. Let's cover all possibilities of 4-bit signed will give me. So that means I will have something from positive 7 to negative 8. Something like that. So actually, to be accurate for 127 that you asked Noah, right? So you have a positive 127, negative 128, maybe something like that. If I look to the number, yeah, it should be. Anyway, I will check for you. But let's go to the positive 6. It will be the same, right? Positive 5, same. Positive 4, same. Positive 3, same. Positive 2, same. Positive 1, same. Now we are coming to our lovely part. Look, positive 0. Same. Negative 0. What will happen? There is no 2's complement for the negative 0. Okay, there is nothing called 2's complement for the negative 0. It's not exist, right? And so you say undefined. 2's complement, this is 2's complement, so you just take it as this, and it's undefined. Magnitude of it is gonna be what? Okay, that means the value and the sign. Now, the first complement of it, it can happen. Okay, so the first complement of it can happen. Guess what? It's a negative like this, right? This is the value, right? And you flip, right? Rules was flipping for the complement, right? So, every single 0, it will be 1. Every single 1 will be 0, excluding the sign. Excluding the sign. You cannot flip signs. How is it possible for you coming to my office with +7. You will get out with -7. It doesn't make sense. You still have it in your pocket. So basically, it's going to be here 1 moving, and everything 1 and 0 here, which will be flipped. So you're going to be 1, 1, 1. So in that case, I can write in front of that 0 for the ones complement 1, 1, 1. So far, so good. So this is for the -0. Even I'm not going to use it. -0, it helped me to understand what I'm going to do with the rest of the number in negative. That makes sense? So if I go ahead now and say now -1, that's a straightforward value with negative, right? So going to be here -1. So -1 for me is going to be in the sign magnitude. It's a 1, 1, 2, 3, 1, 2, 3, and 1. Right? So this is the value 1, and this is the sign. Now let's get the ones complement and twos complement, right? So the ones complement is very straightforward, right? It's basically the 1 will be 0 and is 1, 1, 1. And there is this one, as I said, it's going to be reserved, right? So in that case, it's going to be what? 0, 1, 1, 1. You add 1 to it to be twos complement, so it's going to be 1, 2, 3, 4. And you will move forward. Any questions so far regarding this part?
Professor?
Yes.
Just remember, why didn't you flip it? What you just did.
What do you mean by flip?
To find the first complement, you kept the one which is the sign. Why didn't you flip the other side? For it to become 001.
You mean like this?
No, you remember to find the first complement, we flip it?
Yeah, why? You know why you will flip, right? You don't know why you flip?
I'm asking why didn't we flip on this one?
The most significant bit.
The sign. The most significant is the sign. You cannot flip it.
So you don't.
The most significant is the sign.
Yeah, the most significant is the sign. You have to reserve it now because this is a sign value. So you are not allowed to flip sign.
And why? Can you explain again why the positive don't have the second complement is the same thing? Why for positive second complement?
Oh, because the complement is used for actually flipping negative to positive. But you are positive. Why are we gonna flip it?
Okay.
You understand my point?
Mm-hmm.
Because in the computer, there is no way to say A minus B. In the computer, we say A plus B complement plus 1. This is the twos complement. Okay, and we're gonna learn soon something is called adder, and rebel carry adder, carry look ahead adders, and how those guys work, and all of these things. Okay. Anyway,
Professor, I have a question about just quickly about when you're differentiating the difference between the magnitude and the signed bit. Does the location of the signed bit, when you're trying to so say I'm just getting a bit stream from just a random whatever sock or something like that, and I need to basically differentiate everything that's coming off of it and determine which one is the signed bit and which ones aren't, like the actual magnitude. Does it necessarily mean that whatever you're working in has to be in a set bit value? So I have to know that the sock is working with an 8-bit or 16-bit?
I will tell you. Basically, it depends on the designer. For instance, I made a pattern and I put the most significant bit in the middle.
And you can do that. That's perfectly fine. Because I think I have seen that.
I can do it. I can do it anywhere I want, but then, people have to follow my rules. I will give you an example, right? People already agreed together in a standard saying that, the minute is 60 seconds, right?
Sure.
Then, I came one day to the class and I told you guys, I already invented my minute and it's Muhammad minutes and it's 120 seconds. So now I already added a complexity to you, right? Because you have to flip the time everybody use, which is a minute to 60 seconds, to Muhammad times, which is 120 seconds, right?
Mm-hmm. So there's a standard necessarily where the signed bit is supposed to be.
Here in the country, we have something that's called NIST, which NIST, National Institute of Standard and Technology. Have you guys heard about it? NIST. National Institute of Standard and Technology. And of course, everybody's following AFRL, Air Force Research Lab, ONR, the Navy, and military research lab, NASA, all of the special commercial for space like SpaceX, Dragon, whatever, all of those guys, they have to follow standard. So that's actually the standard. But if you build your own system, the reason I made the most significant is not the most significant, and I flipped the sign because I was looking for optimization. But I made a manual so people can understand why I made that.
I would have imagined you would have done that for security reasons, so people can't
What's
read
security?
off of you. Well, like basically you just make it so that you're reading, like somebody tries to just hardware tap into your chip and tries to read serial to understand.
It was for hardware security reasons.
Yeah, totally. That's
okay. Anyway, now we learned signs. Last time we learned how to subtract numbers, and we figure out if there is no extra digit, then we will figure out that it's a negative. That means the value came out, it has to be 2's complement more times, so it will come into the negative form. If we subtract and then we found there is an extra digit came, so that means this is indication whatever as a fixed digit that will be representing the positive value coming from the operation, right? Now we need to do the same thing for the sign. So if somebody came and tell you that, can you please do this process to me? What are you gonna do? Now is no longer unsigned. This is signed with signed, right? How are we gonna do it? So let's do this together, right? Let's fix the representation in 8-bit. So that's gonna be here 8-bit, 8-bit. So 6 and 8-bit are gonna be what? 0, 1, 1, 0. And then there are 4 zeros there because 1, 2, 3, 4, and this 0 is actually representing the positive, right? 13, 12, it was like that. So that's gonna be the 13, and then 1, 2, 3, 4, and this is actually reserved for the positivity of the 13, right? Now, it's a straightforward. These two terms are in a positive form, right? There is no manipulation we have to do to convert to 2's complement and do all of our Yadi tricky, right? So in that case, I just need to make a normal adding, right? So here is 0 plus 1, 1, 1 plus 0, 1, 1 plus 1, 0, and there is 1 here. 1 plus 0 is 1 plus 1, 0, and you have here 1, and they're going to be here 1, and the rest here will be moving forward. That makes sense? So still I'm reserving here my 0. How many bits I have? 1, 2, 3, 4, 5, and 6, 7, and this is the 8. If you flip this to be, so this is 0, this is the positive, and then let's see what is this in equivalency in the decimal. So this 2 power 0, 2 power 1, 2 power 2, 2 power 3, 2 power 4, right? So it's a 1 plus 2, 3, 3 plus 16 is going to be 19, which is basically exactly what we are looking for, right? Because plus 6 plus 13 is actually what? 19. So this is a piece of cake, a straightforward practice. When the problems will arise, when we start putting negativity in the story, right? And we know from whatever we learned in the high school, right? If somebody's telling you A minus B, what is the value is? It's A plus B, right? If it's A, it's basically minus A plus B. So this guy will have B2's complemented and so on, right? So now I'm gonna give you another example and then we'll move to the next step, which is the BCD. This is lovely. This is really interesting. Everything will be negative. So in the -6, -13, and you're adding. So if you have minus a, which is the value, plus minus b like this, what will happen? So you have to do this complement for both. This is the most aggressive one, right? So I know for sure the output coming of this, it will be what? In negative. Because it's no longer in the logical process that you will just add and you will see what is the positive and what is the extra digit and so on. No, you have to compare what signs. You understand what I'm saying? So if you, let's say that you already have here a value and I know this is sign and this is sign. If I build a circuit doing this, I would just take this one and I take this one and I compare them. And then from there, I will know what is my output will be, right? Then I will start doing comparison between this and that based on the sign also. And then I will do the process. They call it signed adder. Signed adder process.
So you would first look at the sign?
Yes.
But what if, so if one's positive and one's negative, then you would just say that.
Then you have to compare values, right? You have
Okay.
to compare the values.
Yeah, okay, so, okay.
So you're going to build something, it's called digital comparator and so on, We're going to learn this later. So anyway, so if I have -6, let's do the practice of actually moving -6 to be what? Represented in the what's called sign reservations. So I have -6 is going to be 0, 1, 1, 0. And then, 1, 2, 3, 4, 5, 6, 7, 8, right? This is my signed value of it. Then, I have to flip it, right? So flip it, so going to be here, every 0 going to be 1, 0, 0, 1, 1, 1, 1, and this is reserved, right? Then I add 1 to it, so going to be 1 plus 1, it's going to be 0, 1, 0, 1, 2, 3, 4, and this is 1 reserved, right? So this is our equivalency of the -6 in the 2's complement. And then I will take the -13 and I'll do the same work as a practice, right? So 13 is basically 1, 0, 1, 1, 1, 2, 1, 2, 3, and 4. This is -13. Flip it. So going to be here 0, 1, 1. Sorry. 0, 1, 0, 0. And then, 1, 2, 3. And I reserve my 1 also. And then I add here 1. So going to be 1 plus 1, 1, 0, 0, 1, 2, 3, and my 1 here. Now the time to add them and see what will happen, right? So I'm going to add this to that one. So positive 0, 1, 0. And then, 1, 5, right? 1, 2, 3, 4, 5, 6, 7, 8. If you add this together, what will happen? So let's add it together. So going to be 1 plus 0, 1, 1 plus 1, 0, and I have 1. They're going to be here 1, and then I have here 1, and then, 1, 2, 3, and then I still have my 1 reserved, of course, because, those two guys are identical. That means the value is 100% negative.
Doesn't that become 0, 0, 0, 0, 1?
What do you mean? I added this to this 1 plus 0 is 1, right? 1 plus 1, 0, and I have 1. 1 here will go with this 2 zeros, it will be 1. 0 plus 1 is going to be here 1, right? You understand the point?
And then, yeah,
then,
and then,
oh, you're adding values. Oh, I'm sorry. So, okay. Then, 1 plus 1 is what? 0. And then, you already have here 1, right? So every time you can have here 1.
Gotcha.
Right? That makes sense? So in that case, this value is representing in what?
2's complement.
Exactly. So you have to flip it. Right? This is 2 power 0, 2 power 1, 2 power 2, 2 power 3, 2 power 4, 2 power 5, 2 power 6, 2 power 7. If you start doing the process, you will find it never be -19, right? So you have to flip it. So flip it, it's going to be what? 0, 1, 0, 0, 1, 0, 0, and 1. Add 1. So it's going to be here 1, 1, 0, 0, 1, 0, 0, 1. This is what?
Sorry, Professor, if you go up a little bit, so do you carry, so what happened to the other one at the end? Shouldn't be another one in front?
Kicked out.
Oh, you got kicked out, okay.
It's a value. It's a value. I cannot put it in the sign, right?
Yeah, because the one, like the 2 power 8, because you'll get 2 power 8, right? Because it's like 1, 1. So you'll carry that one.
I understand what you're saying. Yes, because look,
Okay.
here, 1 plus 1, 0, and you have 1, right?
Yeah.
1 will go to add to 2 ones. It's going to be 1, and you have another 1. That one
Yep.
will go there, and you understand your point. Yes. It's going to be 1, and there is 1. You cannot put it in the sign. Sign is a sign.
Also, you just kick it out? Okay.
Yeah, because you can call it truncated. You truncate it.
Okay, got it.
There is, there is something we're going to learn in chapter 3, maybe it's called overflow. So the computer can reach a point it's called overflow. That means, it cannot think anymore. It will kick out one of their bits and spit it out, and that will affect, of course, in the precision.
Understood. Thank you.
You are welcome, sir. So everything's clear. If it's not clear, I can repeat. There is no problem. The most important thing for me, quality. Not, material.
Could you repeat yourself?
Huh?
Could you please repeat?
Yes, repeat this part.
Yes, please.
Sure. So, I said -6, -13, and here is plus, right? This is a straightforward two's complement practice. Do you agree?
Oh, yes. Microsoft.
So -6, it has to be two's complemented. And I two's complemented here, right?
Mm-hmm.
Then, -13, I two's complemented here. Oh, scheiße, I'm sorry. Here. And then I take this one and this one, I add them. Now they are in a form of addition. The computer will understand them. Then I add them, I got out here something, right? That value is indirect reflect on the -19. So that means I have to two's complemented one more time. Who told you to do that?
It's because of the sign, right?
Exactly.
Yeah.
Yes. But when you add 1 and 1, oh, that's the sign. You don't really actually add it. You just like reserve it and put it back down there.
Exactly. Definitely, yes.
And what did you say about the answer we had down? We have to flip it again because
this is negative. So that means, this value, it has to be two's complement one more time. And that one will be representing this negative. See, I made it negative like this, right? And whatever will come here will be the value. And if you check this value, you will find a 19, which is correct. If you say -6, -13 is what? -19.
okay.
Okay, Luke?
Yeah.
Any other questions before we move to something really interesting? It's called BCD. Okay, now we're gonna move to another way of representing values. It's look like a binary, but it's not a binary. And this one, it's called BCD, which stands for the binary coded decimal. What is BCD? So BCD came into a conclusion which is really crazy. Every single digit in decimal, it's 0 to 9, right? But if I would like to convert any 0 to 9s, it's gonna be converted to what? To 4 zeros or 1001. That makes sense? So it's the rule said, every digit in decimal is between 0 to 9. If I would like to convert this 0 to 9 to binary, how many bits I need to represent them? 4 bit. 4 digit of binary, okay? So for instance, 0, it can be represented to 1, 2, 3, 4. 1, 1, 0, 0, 0. Up to 9, which is basically 1, 0, 0, 1. Make sense? But 4 digit it can actually represent 0 to 15, right? If somebody tell you I have 4 digits of like this is X, like location of it, 4 digit of binary. So that means this can be bunch of 0 or 1s. 0 is actually 0, 1s is 15. Sounds good? So how many digits between 9 to 15s I have in my hand? Somebody can tell me? How many value that I'm not representing between 9 and 15s now in this part? 10, 11, 12, 13, 14, 15. Six numbers are out, right? I want you to put this 6 number in your hand now, and later we will know why. But at least you know there is 6 to return it back to 0, right? Because if I have 4 locations that can go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and then back to 0. So I have 6 locations here. Anyway, the second part of the representation, if somebody telling you I have 185 in decimal, this is decimal, right? And I'm asking you to convert it to BCD. I have 3 digits in decimal. I want to convert it to BCD. What is the process? I will look to every single digit by itself. So this is what? 5. This is 8. This is 1. And I will go in my table here, which is taken 0 to 9, and I put the value there. So 5 here is what? 1, 0, 1, 0. 8 is what? 1, 2, 3, 1. 1 is what? 1, 0, 0, 0. So whatever in front of you is the BCD equivalence of the 185 in decimal. Do you want me to repeat?
Professor, can you repeat what you said about the 6 values?
The 6th value is something I want you to put it in your hand and just in your mind. I already represented 0 to 9 in a 4 location, 4 digit and binary. Do you agree?
Yes.
And it stopped here in 1001. But in reality, those 4 locations can actually fill up to 111, right?
Oh yeah.
Do you agree? So that means 10 is not here, right? 11 is not here. 12 is not here. 14 is not here. 15 is not here. So that means how many locations are not here?
6.
6. I want you to put this in your hand now.
Okay.
Okay. Later you will know why. So one of the questions I can bring in any exam, or any other of the colleagues give you an exam, say that here's the value in decimal. Go give it to me in what? In BCD. Or somebody else can come and tell you, here is a truncation of binary, and I want to see the BCD. What are you going to do? So you understand what I'm saying? So this is one of the way. So I have decimal, and I move it to what? To BCD by taking every single digit by itself and moving into what? Into the BCD by portion. Here is another thing. I can use the 6-bit 6 location I mentioned. So imagine somebody wrote you this following code: 1111. No, let me do it in a different way. Boom, boom, boom. 11101 1 2 3 4. I'm sorry. Let me find you an example. From the book. I need example. Okay. 1110 111 0011 11001110. And they told you this is a binary number. Okay, this is a binary number, and I'm asking you to give me the BCD equivalency of this number. What are we gonna do? So every 4 digit of the binary will be giving me a digit in the BCD. Do you agree? This number is what? 7 between 0 to 9. Do you agree? So I'm going to put it here as a 7. This number is 12. But, you know, Professor Ali said, you know, I have 0 to 9. Put it in the side. This number is 3, right? 3 is 3. Put it. This number is what? 6. Put it 6. Now we will back to 12. If you like to get 12 back to 0 to 9, you have to add 6. That's called modulo. Have you guys heard about this form? It's called modulo.
I have not. Nope.
So if I say x modulo 9, I will get the value.
You receive the remainder?
Yes. So in that case, 12, it has to be added to what? 6. Let's add it together, right? So going to be here 0, going to be here 1, it's going to be 1 plus 1 is 0. And then, you know, I have here what? Sorry, 0, 0, 1, and then, you know, 1 is 0, and then, you know, 1 here is 0, and there's this 1 extra here. Do you agree? This 4-digit will be here. This 1 will go there. So they're going to be 4. So this number in front of you is representing what? The BCD equivalency of that number. Any questions so far?
Why did we add it by why did we add the 12 by 0 1 1 0?
Because, you know, it's a ring. They call it ring module. What does it mean? I have numbers 0 to 9, right? I need to stay in this ring, right? How can I return it back to this ring? I have to go, if I am outside the ring and it's still in the 4-digit, I have to add 6. So think about it, right? If you are 10, right? Add 6, what will happen? You return it back to 0. If you are 11, add 6, what will happen? You will be 1. If you are 12, add 6, it will be 2. You know what I mean? That's a modular ring. It's like a ring. I need to stay in this circle. So help me to do that. Any number, because, you know, 4-digit would never actually process more than 15, right? 4-digit, 4 location in a binary, maximum it will be 1111, right? Which is 15. But I want to hit back to 0. How can I do it? I just like flip like this. So you have to add 6. Anyway, if it's not clear, I can repeat. If it's clear or not clear.
So this is only BCD, right?
That's a BCD, yes. So I give you another thing. Imagine somebody's telling you 448 BCD added to 589 BCD. Okay, so 448 to 589. Those are 2 BCDs. I need to do a process of adding and subtracting. Adding and subtracting here is like easy, like you just add and subtract. Okay, so if I add, then I will go here and say, you know, it's 8, here is 9, it's 4, here is 8, it's a it's 4, here is 5, right? Then I will move a little bit. 8 is 1, 2, 3, 1. 4 is 0, 0, 1, 0. 4 is 0, 0, 1, 0. 9 is 1, 1, 0, 1. 8 is 1, 2, 3, 1. 5 is 1, 0, 1, 0. Right? Now I'm going to process adding. So 8 plus 9, what the value will be? So going to be here 1, 0, 0. 1 plus 1 is what? 0, and I have 1 will go here. That makes sense? So that one will go here. Now, that one will be added to gonna be 1, 0, 1, 1. Then you know those guys are together, so gonna be 1, 0, 0, 1. That makes sense? Now, is this number within the ring 0 to 9 or not?
Yes, it is.
Yes.
Okay, so gonna be 1. Is this number within the 0 to 9 or not?
It's not.
It's not. So we have to add what?
6.
To return it back to the ring, right? So I'm going to add here 0, 1, 1, 0. This number is what? 9. It doesn't need to be added to anything. I will just move it as it is now. Anyway, we can actually leave this, so we can just make it one shot. Anyway, I'm going to move forward. So this value is going to be still the same. Same. This one, 1 plus 0 is what? 1, 0, 1. 1 plus 1, 0, and I have 1. 1 plus 1, 0, and I have 1 here. That one will be here, 10. That makes sense? Now, I'm going to move this one within the 9 or not? It is 1. This one now is within the 9. This one is not within the 9. So I will add what?
6 again.
Exactly.
Professor?
Yes.
Sorry, but I'm bringing us backward a little bit. Can you go again over why is it 6? Because I tried to do it myself and I don't stay.
Okay, I will tell you why it's 6. Now BCD, it's 0 to 9, right?
Yes.
How many bits you need to represent 9?
4.
4, exactly, which is 1, 0, 0, 1. But 4 representing how many possibilities?
1, 0 to 15.
Exactly. Is there any 15 here?
No.
No. So basically 1, 2, 3, 4. So the scientists come and say, okay, I have 0 to 9. But you know, in possibilities, I can have 10 and 11 and 12.
Oh.
But those guys are not exist in this ring. I have to go back to the ring.
Oh, so the 6 is the 6 you told us to hold on to before?
Yes, because you know, exactly, because you know, 10, 11, 12, 13, 14, 15, those are 6 elements.
I forgot about it. Yeah. Gotcha. Thank you.
You're welcome. So is it clear so far?
So after I did that, I got a remainder, not a remainder, but it's a larger number. So does it get rolled over to 0, 0, 0, 0? The answer for the question.
Let me see. I don't know why my tablet is like stuck. Huh? Oh, now it's moving. Okay, it's the glitch. Okay, so what do you say again?
So what would be the BCD total?
You will just keep adding until you know the whole thing will be done, right?
Yeah. So yeah, I added it, and then
It's gonna be here 1. You're gonna be here 3, and
Yeah.
10 plus 6 is gonna be 16s, right? So it's
Mhm.
gonna be 0, 1. That's your BCD.
Oh, okay. So it is 0, 1.
Okay. Let's do one more time. You know, we still have 17 minutes. So another one, which is 184 BCD plus 576 BCD, right? So that's really quite straightforward. More people are missing here or what? No, I don't think this is actually part of the lecture. Anyway. So 4 are gonna be 0, 0, 1, 0, 8.
Sorry, there's a question in the chat. They're saying that so the answer for the last one is 1031.
This one.
So sorry, where did you get the 10 from?
Okay. Did you see this 10? It's 10 between the 0 and 9?
Yeah, you added a 6 onto that, right?
Exactly. Okay.
So,
yes.
Wait, so if you add a 6 to it, that
So
will
6
give
plus
you
10 is what? 16.
we can't represent that.
We can't. Why? 16 is basically 16. 1, 2, 3, 4, and 1. This is 4 group as 0, and that one with bunch of 3 zeros will give me 1. Because 1 back, right? You forgot about the carry trick?
Oh no. Yeah, I saw that 000. Okay, got it. Okay.
And the second example will make it easy, okay? Anyway, so this is actually what we're talking about. What? 4, 8, 1. Right? The other one is 6, 7, and 5. Right? Normal addition. So 0, 1, 0, 1. We're gonna have a problem here a little bit, right? Then here it's gonna be 1, 2, 3, 4, F 15. More problems. Here we're gonna be what? 0, 1, 1, 0. Right? Are we done? No, we have to make modification. Every single digit is gonna be added to 6 here, right? So I have here 0, 1, 1, 0, and here 0, 1, 1, 0. Here nothing, because it's actually normal, right? Then this is per digit. So 0, 1 plus 1, 0, and I have 1. 1 plus 1, 0, and I have 1. That 1 will go with this one. What will happen? They're gonna be 0, and that 1 will go here. Now 0 cleared up is ready for us to what? To use as a BCD. Okay, now this 1, 1, whatever, it's gonna be added, right? So 1 plus 1 is what? 0, 0, and I have 1. That 1 will go here. So gonna be 1, and I have 1 in my hand. That will be 1, and I have 1 in my hand. And then that will be 1 here. So gonna be 0, and I have 1 here. Right? Then that 1 will be added to 0 to be 1, 1, 1, 0. So 0 is 0, 6 is 6, and this is 7. So this is gonna be our BCD equivalent, 716 BCD. That makes sense? Any question?
Sorry, you just went a little bit fast there for me. I'm just calculating the 16 right now.
Easy. 184, right? This is
yeah, I got that.
4. This is 8. This is 1. Right? 6 is what? Here. 7 here. And 5 there. Do you agree? Now I'm adding. This is 4 plus what? 4 plus 6 is 10, right?
Yes.
This is 10.
Got it.
Okay. Now, this is 8 plus 7, 15, right?
15.
Here's my 15.
1
1 plus 5 is what? 6. Right? Now, I cannot buy this as a BCD. I have to take every single digit back into 0 to 9. So I have to add 6, right? Since this is 10, it has to be added to 6. Since this is 15, it has to add it to 6. Make sense? Now, 10 plus 6 is what? 16, right? 16, that means 40, and the number 5th digit 1 will go here. Right? Then 15 plus 6 is what? 21, right? 21 plus 1 is what? 22, right? If you loop it back multiple times, it's gonna be 6, right? Don't worry about all this number. 1 here is up here, right? 1 plus 1 is what? 1. 0. 0, 0, and I have that 1 here, right? 1 plus 1, 0, and I have 1 here, so it's gonna be 1, and that 1 will go here. This 1 will go with 1. It's gonna be what? 0 plus that 1. It's gonna go here, and there is 1 here. So 1 plus 1 is gonna be 0, 0, 0. But then extra 1 will move there, so that 1 will be here, right?
Yeah.
Then, okay, I will start looking.
You just bring it down 7. Got it.
Yes, sir. So this 0 within the 0 to 9 represented. This value is 6 within 0 to 9. Now that 1 plus the 6 is what? 7. 7 within the what? 7, the 0 to 9, right? So put it there. So now I'm done. I don't need to add any more. So it's 760. So yeah, somebody said, catch up, chef, what? To get it back in the 0 to 9 digit. Yes, that's called modulo. I didn't know that you guys didn't use this in the high school. Have you heard about modulo?
I did not know.
It's called a modulo ring.
It's typically
Modulo ring, that
percent.
means, any number within the ring, any number outside the ring, it has to return it back to the ring. You understand my point?
In like coding languages, it's typically represented by the percent sign. So you
Yes.
take the modulo of something.
Yes. And by the way, in the beginning of the lecture, I was talking about sign unsigned, right? In C, there is something that's called variable signs and variable unsigned. Make sense? Any other questions? Now, we can talk still. We have 10 minutes. Oh, we have a lot of time. That's good. So there are other mathematicians came with building other systems. Okay. Some mathematicians came and they build the BCD, right? They build something is called Excess-3. Excess-3. And some other, they build something is called 2421. Somebody make it 84 minus 2 minus 1. I mean, somebody, whatever he wants here, right? So what is the story behind those guys? Those guys, part of the, how to say, those binary codes. So that's called binary code. They try to make it easy to make it more binary. So professor, so is there a homework or do we practice? Practice. I mean, homework is just like numbers, right? And there's in the book here. That's why I shared with you in the beginning of the lecture. Do you remember? I shared with you the book material, right? So you will find here problems here. They have under this chapter 136. They have 36 questions. You can just pick up the questions belong this number system and practice. And if something stopped, you can just ask and I will help. That makes sense? And if I run faster a little bit and finish chapter 2, I can make like a review and play with some examples if you want. Anyway, so excuse me. What is the story behind those three guys? Those actually part of the binary coded system. So when I say binary coded, that means I'm dealing between decimal and binary. That's it. And why is it formed in a 4-digit like this? Because, remember 0 to 9, right? So imagine the following. Somebody told you, I have a system is called 2421. In a normal binary, it was 2 power 0, 2 power 1, 2 power 2, 2 power 3. Do you remember that? And somebody told you, I have a value 8. And I want you to represent this 8 using this system. So what are we going to do? 8, it can be represented using what? 1, 1, 1, 0. Because, 2 plus 4, 6 plus 2, 8. Right? So that's one of the examples. But, the most common one, which is not completely vanished, nobody is, the rest of those guys are not used very commonly. This one is used like commonly. That's called Excess-3. So in Excess-3, you add 3 to every single digit you have in the BCD. That's just Excess-3. So what does it mean? It means if you are 0 to 9, 0 in Excess-3 would be 3, and 9 will be 12. And anything in the middle would be, of course, incremented by 3. That's called Excess-3. So if somebody, for instance, told you that I have 184 in a BCD and asking you to give me my Excess-3, what are you going to do? You're going to just add 3 to each, right? That's it.
So do we first convert it to binary first and then add 3 to that?
Yeah,
Or
you can do this, or it's
that?
easy, I mean, you can do that of course, You can convert it, or it's easy. You can just flip it. But I think,
or do you just add 3 to that? So that would be like 7, 12 would be.
So I will tell you what.
Yeah.
Basically, no, the table is like you already have decimal, and you already have here BCD, right? And then you already have here the Excess-3, right? So that's like this. I have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Do you agree? Now BCD is the same, right? So gonna be 1, 2, 3, 4, up to 1, 0, 0, 1, right? Now Excess-3, no, this one will be incremented by 3. So gonna be 1, 1, 0, 0. 1 will be 4. 2 will be 5. 3 will be 6. 4 would be 7. Up to here, we're gonna be 9 will be what? 12. The rest here, exactly like the BCD, are not used. Also in the decimal, there is no 10 and 11 and 12, right? So this area is what? Unused. So what you're gonna do, you're gonna take whatever and you equivalent it by 3. And you know, let's say that 3, you equivalent it by 3, 6, right? And so on. That makes sense?
Yes, thank you.
That's called binary coded. I'm just showing you some other systems. You know, by the way, you can build your own systems. If you understand the trick, you can just build a system, you know. But still, who's gonna use it? So you have to make it popular. Okay. Now, there are 2 things I like to give you, but it depends on the time because, you know, I like to finish the chapter, but I don't think I will finish it today. Anyway, there is something called gray code, and there is something called priority bit. Gray code, priority bit. So the gray code has a story. I will just talk about it and then I will repeat it next time. Gray code has story. You guys know that's like in decades, there was no like communication between of the Atlantic Ocean sides, right? Like Europe and United States, right? There is no way for you to send a signal from the States. It will go to Paris and head back to United States. And Gray was a mathematician, and he said that, you know, when they start sending this electromagnetic waves and radio and all these things, they come and say communication can be degraded by the environment and the atmosphere, you know, and all of these clouds and, you know, whatever, you know, lighting and sparks or whatever. So he came into the conclusion that, you know, I would like to send the data with a small distance changes between of the neighbors. What does it mean? So he means that, you know, I would like to send, if I would like to send 4 and 3, right? In a binary, 4 is like this, right? 3 is like that. What you can understand from this, that means there are 3 switches have been changed, flipped. Do you agree? Because, you know, 0 turned to 1, 0 turned to 1, 1 turned to 0. Each one is switched, right? 0, 1. So that will increase the chances for something is called what? Error or damage in the data packets. Gray said no. Neighbors should have 1 changes. That means I'm gonna change 1 switch per neighbor. How he already did that? Let's see. So basically, no, he came into a conclusion, say that, you know, if I have a BCD 0 to 9, okay, which is basically 1, 2, 3, 4, up to 1, 0, 0, 1, right? He came and say, I would like to convert it to what? To my own code. It's called gray code. Let's make an example and see whether the guy actually did the right thing or not. So let's pick 3 and 4 as we did, right? So 3 and 4, if I look to 3, it was 1, 1, 0, 0. And 4 for me, 1, 1, 1, 0. So this is actually 3, and this is 4. For Gray, this is a big problem. So he came into conclusion, say that, you know, I need to move, if you imagine this is B0, B1, B2, B3, I will build my equivalent to be Gray 3, Gray 2, Gray 1, Gray 0, and I will start making the work. How can I do this? So the guy came and say Gray 3, it should be B3. So as it is, the most significant will be taken as it is. And then neighbors will be added to each other without carry. So what does it mean? That means, you know, Gray 2 will be B3 plus B2 without carry, This one is going to be moving forward to be B2 plus B1 without carry. This one will be a B1 plus B0 without carry. Let's make a practice, and then, next time I will do it one more time. So let's apply it on 3, right? So I have 1, 1, 0, 0, right? So Gray said, take this as it is, so going to be 0. Then add this together to each other, they're going to be 0. Then, add this together to each other, going to be 1. Then add this together to each one, going to be what? 0, and there is no carry because the 1 will be kicked out. Let's take the 4, right? 4 will be 0. This takes together, going to be 1. Let's take this together, we're going to be what? 1. Let's take this together, we're going to be what? 0. So let's look at the neighbors here. 0, 1, 1, 0. If we start checking, they are the same here, they're the same here, they're the same here. The only flip happened in what? In this position. That means he made it what? One distance switch changes, which is preserving the data. Do you guys have any question?
Can you convert that back into binary? Because you don't know the carried numbers anymore.
It's not important for him. The most important for him, it was to broadcast the data with lower rate of changes. So
Okay.
it will be easy for him to reverse engineer and find out what was the error.
Okay.
But we can make a mechanism for returning it back if you want. It's not really like a rocket science, it's doable, right? Any questions? We are actually finished because it's 2:16, so that means I borrowed 1 minute from the other people. So that means I would like to thank you guys for the time and effort and for attending the class. I hope you guys are enjoying the class. And if you have any questions or any problem, don't hesitate, just contact me and I will do my best to help you. A copy of the note with a copy of the recorded lecture will be posted tonight, roughly by 8 or 7:30 p.m. once I finish my teaching day. Any questions?
No, thank you, Professor. Well, just a quick question. It's like, where do we use the grade code?
This is for communication, especially if you are working with satellite communication. There is a story. Do you guys have a minute so I can tell you a story about the satellite communication? Or you guys don't have time? It's up to you.
Oh, maybe next semester. Oh, sorry, not next.
Next semester, okay.
Next.
It's up to you guys. I mean, if I know that you guys are busy, so maybe we can talk about. Somebody remind me about it, and I will tell you the story. Okay.
Sounds great for me. Thank you.
Okay, guys. Thank you. God bless you. See you next time.
Professor.
Thank you.
Professor.
Bye.
Thank you, Professor.
Have a good one.
You too. Bye. Sorry.